For topic 6, we're going to talk about exponential form of a complex number. So that one's kind of new. We haven't talked about exponential stuff yet in our journey in chapter 10. Okay, now this is a situation where I don't like to tell you just trust the process. This is one where it's kind of like just trust the process. This isn't something that outside of this right now, I don't know. I'm trying to remember. I feel like this comes up higher, much higher in math. So you may not see it in the near future, but sometimes just having exposure to it and like understanding that, hey, this is really what you're going to see. This is just a game of subbing numbers in. Okay. There's nothing really scary here. So don't get too bent out of shape about this. Just trust the process. It is just a formula that we're going to do. We're not going to look at any kind of a proof of it. We're just going to trust the process. Okay. So we have Euler's formula. Okay, for any number theta in radians. So we do need to understand that this does need to be in radians here. Okay, but for any number in radians, we have e to the I theta equals cosine theta plus I sine theta. Okay, we're not going to prove this at all. We're not even going to try to think about proving it. We're just going to take it for what it is. Now remember, e is one of those irrational numbers, kind of like pi. It's like 2 point, let me see, I don't even remember, 2.7 something. Whoops, on. It is 2.7182, blah, 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 blah. Okay, so again, it's just an irrational number. We're not even really going to have to deal with it. We're just going to plug numbers in and simplify our formula. Okay, so e to the I times theta equals cosine theta plus I times sine theta. Okay, now from this, we can convert the polar form of a complex number into exponential. So it does need to be a situation where you already have polar and then you can convert it to this exponential situation. And what we get is this. Okay, so really all we're doing is we're taking this Euler's formula and we're basically, is it going to let me? There we go. We multiply this by r, and we get exponential form of a complex number that was in polar form. Okay, so therefore z equals r times e to the I theta is considered to be the complex number in exponential form where the value of theta is measured in radians. So we've said it here now twice. So we do need to make sure that if for whatever reason we're given theta in degrees, we if we're doing this exponential form, we really do need to convert it to radians. Okay. So, with that said, let's mosey and look at some examples. I think I have, is this the one? There's a few examples here, so this is going to take just a minute, okay? So it says, for example 11, consider the following complex number. We have that z equals the square root of 3 minus I. Well, this, I could think of it if you need to, as z equals the square root of 3 minus 1 times I, just in case. Like, remember, we don't write those coefficients of 1, okay? So there is a 1 there, all right? Now, it says write z in polar form. Well, here's the thing. When you're taking something that's in rectangular form, think of it as like x's and y's. So remember, we can think of this as z equals x plus y I. So this is our z, or this is our z. This is our x, and this is our y. Okay? Well, if we want to write it in polar form, we need r's and thetas. So we technically have x and y. We need r and theta. So if we can get r and theta, we can get polar form. Okay, so please remember a couple of things. We need to remember that r is equal to the square root of x squared plus y squared. And then we need to remember that tangent of theta equals y over x. That's how we find our r and how we find our theta from something that's kind of in like this rectangular form. Okay, so let's talk about r. I like that purple color. It's very pleasing to me. So I'm going to go back to this like plum purple color. So r is going to equal, remember, it's the square root of x squared plus y squared. This is our x. This is our y. So we're going to get the square root of 3 squared plus negative 1 squared. Well, the square root of 3 squared, that's just going to be 3. The square root and the exponent of 2, they just unravel each other. And then negative 1 squared, that's just 1. So we get the square root of 4, which is really 2. So we can say, well, I'm just going to write it like this. We can say that r is 2. Okay. Now, to get theta, we have to use the fact that tangent of theta relates a y and an x. And that's super for us because we have a y and we have an x. So we're going to say, okay, tangent of theta equals y over x, which means that theta is inverse tangent of y over x. Okay, so let's find inverse tangent of our y over x. So theta equals inverse tangent of, well, y is -1 and x is √3. So we've already talked about this in this worksheet, but just in case you have forgotten, envision the unit circle. Remember, inverse tangent is defined only from -π/2 to +π/2. So we're going to have -π/2 to +π/2. And because this ratio in our argument is negative, that tells me we're going to be in quadrant 4. Okay, so in quadrant 4, we have basically two values for theta that we can worry about. At theta equals -π/6, we have the point √3/2, comma, -1/2. We want to see if that gives us the proper tangent ratio, which is -1/√3. So let's see. And remember, tangent is y over x, sine over theta, however you want to think of it. So we have -1/2 divided by √3/2. Well, that's -1/2 times 2/√3. Well, the 2's cancel, so that's -1/√3. We don't even have to rationalize it. We can just say, hey, we know we're at -π/6. So we can say that theta equals -π/6. Okay? So we have basically finished this, but we need to remember, so let's mosey back a smidgen. It's actually going to be a good bit that we have to mosey back. Let's see, one more. Okay, so when we were first learning about polar form of a complex number, we were like, hey, this is polar form of a complex number. We need an r, we need a theta, and then it's just r times cosine theta plus I times sine theta. But we had conditions on r and on theta. We needed to make sure r was positive, and we wanted theta to be an angle between 0 and 2 pi. Okay, well, if we go back to the problem that we have down here, we have theta is not between 0 and 2 pi. So what we want to do is we want to take theta and just add 2 pi to it. So if we have negative, let me erase that and write it better. So if we have -π/6, we want to add 2 pi to that. And if we have a denominator of 6, 2 pi is going to be 12 π/6. So we're going to add 12 π/6, which gives me 11 π/6. So this is my theta. Okay, so just be really careful. We do want to make sure that r and theta are very specific values. So r positive, theta between 0 and 2 pi. So finally, it took us a little bit of work, but we can now say that z, remember we want it in polar form, is going to be r, which is 2, times cosine of theta, which is 11 π/6, plus I times sine of theta, which is 11 π/6. And that's it. Okay. So it takes a little bit of work. All right. You've got to find r. That's pretty easy. Finding theta, you have to use the inverse tangent. Remember, inverse tangent is defined from -π/2 to +π/2. If you are given a value in quadrant 4, that's going to be some negative angle from 0 to -π/2. You just have to add 2 pi to it, and it's going to give you a coterminal angle that is from 0 to 2 pi. Okay. Now, once you have polar form, exponential form is a breeze. Okay. Now, we need to remember that exponential form okay, we have that it is equal to, well, let me show you. I don't want to just let you believe me. We want exponential form, which is this right here. So r times e to the I theta, okay? So r times e to the I theta. Remember, r is 2. Theta is 11 π/6. So we're going to get 2 times e to the I times, that's so stupid looking. Hold on. Let me write that better. We get I times 11 π/6. You could, I guess, if you wanted to, write this as 2 times e to the 11 π/6 I. Just make sure your I is like separate from your 11 π/6. So there you have it. Getting polar form is going to be the harder one because of that angle theta. But once you have polar, Exponential's a breeze. You just have to plug two numbers in, okay? Now, example 12, we're going to be given exponential form. We need to find polar form and we need to find rectangular form. And I guess I'm okay with this. I feel like rectangular form, we should have probably done it first, but we'll get polar form first. That makes more sense. Okay, so we have example 12 says consider the following complex number in exponential form. We have z equals e to the I pi. Okay, now polar form, we need r and we need theta. And we have to remember that we have r times cosine theta plus I sine theta is going to give us r times e to the I theta, okay? So it's pretty easy to find r and theta, okay? So in this particular case, we have, I'm going to rewrite it just so it's really clear. We have 1 times e to the I pi. So that tells me r is 1 and theta is pi, okay? So this is going to be pretty easy to get polar form. So we're going to get just 1 times cosine of pi plus I times sine of pi. And that 1, it doesn't really do anything for us, so we can just say it's cosine pi plus I times sine pi. And that's it. So this right here is z. It is our complex number in polar form. Now, rectangular form, we've got to do a little more work, okay? So rectangular form, remember, we need x and y, okay? Well, so far, we just have r's and thetas, but for rectangular form, you need those x's and those y's. So remember, x equals cosine theta. Whoops, don't put that. X equals r times cosine of theta, and y equals r times sine of theta. So let's figure out what x and y are. So x equals, well, remember r is just 1, times cosine of theta, theta is just pi. So remember, if we have the unit circle, pi radians is like over here, right? And this point on the unit circle is -1, 0. So what is cosine of pi? Well, cosine of pi is -1. So x equals 1 times -1. So x is just -1. Okay? Now, y is r, which is just 1, times sine of theta, which is just pi. And remember, we've got our unit circle here. Okay, so this is our unit circle. We have this point -1, 0 at pi radians, and we have that sine of pi is just 0. So we get y equals 0. So we want to write z, that's our complex number, in rectangular form. So remember, z equals x plus y I. So just plug in these values. We would say z equals -1 for x plus 0 I. And that's it. Okay, so finding rectangular form isn't too bad. You have to find the x and the y, and we've got these values right here. It's generally, for me, a little harder when I have to find my theta value. Okay, but going from exponential to polar, pretty easy. Going from polar to rectangular, really not too bad. Okay, one more. All right, so we have another one that is in exponential form. So we have example 13 says, consider the following complex number in exponential form. We have z equals 3 times e to the I times 5 pi over 3. It's kind of a mouthful, but what we want to do is figure out what r and theta are. We can really easily get polar form, and then from there we can get rectangular. So in this right here, remember, if we have z equals r times cosine theta plus I sine theta. That is a complex number that's its polar form. And we know that exponential form is r times e to the I times theta. So what is r in this case? Well, r is 3 and theta is 5 pi over 3. So all we have to do is plug those values in. We have to take this and plug it in here. Okay, so we're going to get z equals r, which is 3, times cosine of 5 pi over 3 plus I times sine of 5 pi over 3. And that's it. This is polar form. You want to leave the angles in there. You want to make sure your angle is from 0 to 2 pi. You want to make sure your r is positive, but you don't want to actually evaluate sine and cosine of whatever that angle is. Just leave the angle in there, okay? When we get to rectangular form, that's where we figure out what sine and cosine of those angles are. Okay, so remember for rectangular form, we need x and we need y. And remember, x equals r times cosine of theta, and y equals r times sine of theta. Okay, so let's see what we get here. X, we're going to get r is 3, so we get 3 times cosine of 5 pi over 3. Let's build a little unit circle, y'all. So we have a unit circle, and 5 pi over 3 is like this. And we have the point down here, which is 1/2 comma negative root 3 over 2. So that is 5 pi over 3. So we would say that cosine of 5 pi over 3 is 1/2. So 3 times 1/2 is 3/2. And now to find our y, we know it's r times sine theta. R is 3. Sine of theta is going to be sine of 5 pi over 3. And we have our itty bitty unit circle over here at the bottom of part A. So we know that sine of 5 pi over 3 is root. It's actually negative. Make sure you get the itty bitty negative. It is negative root 3 over 2. So we get y equals 3 times negative root 3 over 2. So y equals negative 3 square root 3 over 2. Okay, and finally, we want to write this in rectangular form, but remember, this is rectangular form of a complex number. So z equals x plus yi. So we would say z equals 3/2 minus 3 root 3 over 2. Don't forget your I out to the front. And there you have rectangular form of the complex number that was initially given to us in exponential form as z equals 3 times e to the I times 5 pi over 3. That's a lot. All right. Do we have another one or is that one? That's a previous one. I'm making sure we haven't left anything out. I think we're good. We move on to the next video where we're going to talk about products and quotients.